Hi everyone, in this lesson we're looking at velocity and acceleration as a function of displacement. So previously we have seen the relationship between the displacement of a particle called x, and that's as a function of time, and the velocity of a particle, so the speed and direction, and the acceleration of a particle. And now these are all being expressed as a function of time. So for instance, the displacement function could have been something like t cubed plus t, for instance. So our displacement function is a function of time. And as to is the velocity function and the acceleration function. Now we're going to learn to relate the velocity, acceleration and displacement to each other and basically eliminate the parameter time. So previously when we looked at acceleration, velocity and displacement, we saw that if we differentiate the displacement function with respect to time, we will get the velocity function. So the velocity function is basically the rate of change of the displacement function with respect to time. And likewise, if we differentiate the velocity function, we will get the acceleration function. And we can also go in the opposite direction. So if we're integrating the acceleration function with respect to time, we go back to the velocity function. We integrate the velocity function with respect to time. We go back to the displacement function. So that is, that's hopefully the assumed knowledge you have coming into this lesson. And now we're going to look to express these in terms of each other as opposed to time. So before we do that, we'll derive a few important identities. So the first one here, we're going to have a look at this, dv dt. So the rate of change of the velocity with respect to time. Using the chain rule, we can break this up to dv dx multiplied by dx dt. So all I've done there is used the chain rule and broken that up. And so what we can note here is that dx dt is actually v. The rate of change of the displacement with respect to time is just v. So we can write this as dv dt is equal to dv dx times v. And generally you put the v at the front, so you'll write it like this, v dv dx. And dv dt over here is just the acceleration. The rate of change of velocity with respect to time is just the acceleration, so we can write a in that. So acceleration, the acceleration of a particle is equivalent to v dv dx. So there's a useful identity there. So that's one of the two we're deriving. Now in the next one, we are going to break up v here, and it's a little bit tricky. So what we do is we're going to write v as dv, d dv of a half v squared. Because if you differentiate this with respect to v, you're just going to get v anyway. So we haven't really changed it, we've just written it in a different form. And we still have times dv dx at the end here. So what we have here, again, is another expression for the acceleration. And using the chain rule, we can almost reverse chain rule and we can condense this into one term a little bit more. And what we get is up here, we'll get the acceleration is equivalent to d dx of a half v squared. So we've derived two identities here for the acceleration. So the acceleration is equivalent to this here. So whenever you see a, the acceleration, which can also be written as the second derivative of displacement with respect to time, or dv dt, but it can also be written as this. So it can be acceleration is equivalent to v dv dx, and it is also equivalent to d dx of a half v squared. So these are two important identities to keep in mind, and in the future lessons on velocity and acceleration as a function of displacement. We'll be using these identities to help us solve problems and relate these variables in terms of each other and eliminate the parameter time. So we'll leave this lesson here, and the main takeaway from this lesson is to be familiar with those two different identities involving the acceleration of a particle